Continue on here. We are chapter 13, maybe. So last time, the majority of what we sort of talked about there, or really got into, was weak acids. And remember, weak acids, because they're basically weak electrolytes, they will set up a equilibrium. And because they're able to do that, we could, of course, have an equilibrium constant associated with them. And that is just like a normal equilibrium constant. So we'll have our products over our reactants. We obviously still do not include water or anything like that. This is what is sometimes referred to as a Ka value. And a Ka value is the ion association there for a weak acid. Remember that strong acids, like hydrochloric acid, will completely break apart into ions. And because it completely breaks apart into these ions, there's nobody coming back the other way. It does not set up an equilibrium. So, as we talked about last time, pretty much only weak acids will have Ka values. And again, that's one way you can identify if it is a weak acid or not. If you see it on a table, or obviously if you're given a Ka value in the problem, you know for sure it is a weak acid. Also, like we talked about, those 6 sort of strong acids, you could remember those, and it's a really good thing to remember those. Again, just by the process of elimination, if it's not one of those 6, it's pretty much going to be probably a weak acid. So those are good ways to do that. Because it does set up this equilibrium and it is weak, that pretty much means you do need to do a nice table to solve for the equilibrium concentrations. One of the main difference, though, in terms of a traditional sort of equilibrium problem and one of these, is you're really interested a lot of times in the pH. So to get to use the pH equation, you do have to do an ice table to get the equilibrium concentration of the H plus. Once you have that, then you can go into here, obviously, after you do that ice table and get the actual concentration. We will solve these problems pretty much the same way you solve any other equilibrium problem, because they're all the same, really. And again, as I mentioned, I would say probably not going to see a lot of perfect squares on these. So it'll be like an assumption, which we did one before and it worked. And a reminder that we also did one that did not work, right? So you do need to make sure you check your assumption. Or if you don't want to worry about that, you could just straight up quadratic it up and go that way. But the assumption can save you some time if it works, obviously, and it might be a better move. Any questions on any of that there? All right, so we did a couple examples. I think I got one more here to go. Why don't we also calculate the pH of this thing as well? So what's the pH and the H plus concentration of a 0.01 molar HCN solution, where the Ka value is 16? So once again, as we talked about, there's a lot of information a lot of times in problems here. So I see HCN, which is an acid, and I do see a Ka value. So again, that should tell you it's a weak acid. Also should tell you you probably need to do an ice table in this case. We'll start with just the dissociation here of our weak acids. So our HCN is going to break apart into H plus and CN minus. Once again, as we talked about last time, you can definitely still use water on the left-hand side and H3O plus on the right-hand side. Same deal. Initially here, we have our initial concentration of 0.01. We're going to go zeros here. That means our change is going to be minus X plus X plus X. That means when we reach equilibrium, 0.01 minus X, X, and X. Questions on that so far? We could write our Ka expression for this, and our Ka expression would be our products divided by our reactants in this case. And obviously that equals our 6.2 times 10 to the minus 10 in this case. We're going to put our equilibrium line into here. So that will get us x squared divided by 0.01 minus x equals 6.2 times 10 to the minus 10. Once again, this Ka value is a small value, which does allow you the option to try the assumption, and that's what I'm going to do here. I'm going to assume x is equal to 0. Again, we are just removing the x's basically that you're subtracting from a number or would add to a number. In this case, it would be pretty much that x right there. You do need to leave an x to solve for. So that gives x squared over 0.01 equals 6.2 times 10 to the minus 10. I'm going to multiply this to the other side, and then right after I'm going to square root it, and we will end up with 6.2 to the minus 10 times 0.01, and take a little square root action there. And that is going to get me about 2.5 times 10 to the minus 6. Again, we do need to check our assumption here. So we do check our assumption by dividing our x value by the number here we're going to subtract it from. So that'll be 0.01 times it by 100%. And in this case, I think we should be good. You're not even at 0.1%. So you're like 0.025%. So the check here is good. That means if we go back to our ice table here, X does equal the H plus concentration. So that looks like number 2 on our list here would be the right one. We also could calculate the pH at this point, since we do know the H plus concentration. pH would be minus the log of 2.5 times 10 to the minus 6 in this case. And that's going to get us there about a 5.6. Oh, pH. Any questions on any of those steps there? Yeah. So the CN is one of those polyatomic ions, so they'll stay together because omega is a whole unit. Yeah. So pretty much an acid, right? The cation is the H plus. So if you take the H out of the acid, whatever's left over usually should stay together as one type thing and have a charge, a negative charge. Yeah. Other questions? All right, the next thing we're going to talk about actually is percent ionization of an acid, or really even a base. And the percent ionization of an acid is really the percentage of how much H plus comes off, which is what an acid is. We talk about sort of percent ionization of a base is kind of how much OH minus sort of comes off as a result of that. You could calculate the percent ionization by taking the H plus concentration at equilibrium divided by the initial concentration of your acid and times it by 100. That calculation should look familiar to you because we just did it a second ago. That is basically the calculation you do when you check your assumption. So that's basically the calculation that you do to check your assumption. Gives you the percent ionization. A strong acid will 100% ionize. So as you can see here, it's going to completely ionize. A weak acid will basically ionize based on its sort of initial concentration. So as you can see, the concentration is really important. And that's, again, as we talked about the other day, why sometimes your assumption works and why sometimes your assumption perhaps doesn't work. As you can see here, when you have a larger concentration of like your acid, you have a lower percent ionization. And when you start with a smaller concentration of your acid, you have a much higher percent ionization. That was like my pizza example I did the other day, right? So you got a whole pizza, take one slice out, not a big deal. But if you only have 2 slices and take one out, it's a much bigger percentage of what you started with. And that happens with our acids here as well. So you could use this as a formula to figure out the percent ionization of your acid. You could also, for example, the one that we just did there, our percent ionization was like 0.02%, right? So just a little bit of it basically broke them off in that type of situation. Now, let's take a look at this and sort of see how we can maybe use percent ionization for something other than just calculating percent ionization of an acid. So let's say we had a solution of 8 molar formic acid, and it is 0.47% ionized. In this case, we actually want to know what is the Ka value of our acid. So we could actually approach this like a normal sort of weak acid problem. By the way, I do still know it's a weak acid. Otherwise, I would not be looking for a Ka value, right? So again, here I do know this should be a weak acid. So I'm going to start with an ice table like I would normally do. So I'm going to take my formic acid. I'm going to dissociate it into H plus and my formate there. We're going to go initially. We know that the initial concentration here is 8 molar. It's going to be 0, 0. Change would be minus x plus x plus x. And that means at equilibrium, we would have 8 minus x, x, and x. So this is sort of like a normal sort of ice table. We obviously could write our Ka expression, which would be our products over our reactants. And that equals, in this case, what we're looking for. So in a normal situation, right, we would take that equilibrium line and put it into our Ka expression if we knew the Ka value, and then we could kind of solve for it. But in this case, we're actually looking for the Ka value, which means we need to figure out maybe another way that we could solve for it. And we can help us to do that is the other piece of information that was given to us, which is this acid is 0.47% ionized. So as we just saw, our percent ionization is equal to the H plus concentration divided by the initial concentration of your acid times 100%. So we know the initial concentration of our acid, which is right here, and we do know the percent ionization. So if we put those numbers in, I think that here, we got 0.47% ionized equals the H plus concentration. Our initial concentration was 8 molar times 100%. We're going to multiply the 8 to the other side, and then we're going to divide the 100 to the other side. So if we do that, we'll go 0.47 times 8 divided by 100. And that's going to give you a value here of the H plus concentration will equal 0.0376 molar in this case. First off, any questions on that? That's going to help me because when I look at my ice table, very much like you did in experiment 2, was it maybe? I could see that in my ice table, the H plus concentration actually equals X. And that X is the same X as this one and that one as well. So now that we actually know what X is, we could actually put our values in here. And now we could actually get to our equilibrium constant. And in this case, that means that the concentration of H plus at equilibrium would equal 0.0376. The concentration of formate there will also equal 0.0376 molar, as that also equals X. And if we look at our formic acid, that actually is 8 minus X, so 8 minus 0.0376. And that's going to get us here. Looks like 7.9624 molar. So now by kind of using that percent ionization, we're able to find the equilibrium concentrations of everybody. So now all that's left is basically just pop it into our expression here. So our Ka would equal basically 0.0376 squared, since there's both of them, divided by 7.9624. And that's going to get us here. Too many zeros. Let's see. It gives us something like 1.8 times 10 to the minus 4 as our Ka value. So very similar to sort of how you use your calibration curve. Here we can use our percent ionization, kind of work backwards and figure out everybody's equilibrium concentrations, and that allows us to figure out the Ka value in this case. Obviously, you could also use this formula just straight up as that formula and solve for something like percent ionization and just kind of plug in there as well. Any questions on that there? Again, you could also do this for a base. Again, you'd just be looking at the hydroxide concentration rather than the H plus. All right, so we talked about weak acids. So because there's weak acids, I'm sure there's going to be weak bases, and there are. So let's talk a little bit about what happens with our weak bases. So remember that a majority of our strong bases are group 1 and group 2 on the periodic table with hydroxide in it. Pretty much if it doesn't have hydroxide in it, it's probably going to be a weak base. A lot of weak bases also have nitrogen in it, so that's also kind of a good hint. So here's ammonia, which is a weak base. So that's ammonia. And when it reacts with water, it's going to actually accept the H plus from water, and that is what generates the hydroxide in this particular case. Hence why you picked up the bottle today of ammonium hydroxide, right, for ammonia here, and that is what it is, an equilibrium in solution. We could write a K equilibrium expression for this, products over reactants. In this case, once again, we are not going to include the liquid water. So that'll give us our NH4 plus and our OH minus divided by our NH3. That is known as a KB, adding to our ever-growing list of K values, KC, KP, KW, KA, KB. We're not actually done yet. Still more to go as we go through these chapters. Just like our Ka value, the Kb value, as it increases, the strength of that weak base gets stronger. And again, it's for the same reason, because again, if we have a large value of K, that means we should mainly have products at equilibrium. And if we mainly have products, that means that that thing has released a good amount, if you will, of OH minus, free OH minus in that solution, which makes it a stronger, again, weak base than another strong weak base. So again, that's the comparison of two weak bases. Once again, something like sodium hydroxide is going to be a much stronger base than any weak base, because again, all it has to do is go in for a swim and it will produce hydroxide pretty easily. It's just going to fall apart. So it's a much stronger base. Now, to solve these problems, once again, because it is a weak base, it will set up this equilibrium. So once again, to solve for the pH, we again need to do an ice table in this case. The main difference, though, is if you look at your reaction here, you have hydroxide and not H plus. So when you solve for X in this case, in your ice table, that is actually the hydroxide concentration, which, as you hopefully remember at this point, that will get you directly to the POH, then maybe subtract 14 and get yourself to the pH. So a really common mistake that people make is they solve it and they really don't know what's going on, and they try to fake it, and they get their X value and they figure, oh, that must just be the H plus, and go right into the pH. Obviously, in this case, that would give you the wrong answer, as that is the hydroxide concentration. So as I mentioned previously, it's really, really important to be able to write these equations correctly. I can't tell you how many I've seen write this equation and end up with H3O plus on the other side. Yeah. So again, really, really important to know how to write those equations. And you do need to be able to do that on quizzes and exams. But pretty much straightforward assumption, quadratic, get your X value. Here's a table similar to ones you have in your book of some weak bases. As I mentioned before, a lot of weak bases will kind of have nitrogen in it. Not all of them, but a lot of them will definitely have kind of nitrogen kind of floating around in there somewhere. So why don't you give this a try? An amine compound has a bad smell. The Kb is 5.6 times 10 to the minus 4 for this one here, C2H5NH2. What would be the pH if you had a 0.15 molar solution of it? So take a few moments there, calculate up the pH in this case. Yeah.
So, to go kind of back, how do we know if it's a weak base or
Yeah, that would be a good hint if you have either the Ka or the Kb given to you in a problem. If you have a Ka, then you definitely know it's a weak acid. If you have a Kb, it's definitely a weak base. Also, like I said, in terms of the acid, knowing those six, can eliminate and know, which one would be a weak acid if it's not one of those six. In terms of a base, in terms of strong bases, like I said, if it's not somebody from group 1 or group 2 on the periodic table that actually has hydroxide OH in the formula, it's probably going to be a weak base. Yeah, so that's a good way to do it. Yeah. All right, let's give it a go. Okay, let's take a look, see how you're doing. So once again, a couple of pieces of information that should help you kind of focus on what you should be doing. As we've been talking about, I see a KB value. So again, that automatically makes me think weak base. And the second thing you should think about after you think about that is I should do an ice table here. So that's what you want to kind of think about. We're looking for the pH. So we'll start with what was given to us, which is the weak base C2H. 5 NH2. As I mentioned earlier, probably with bases, it probably is a good idea to put the water in. So you could kind of maybe just think about it as a Bronsted-Lowry sort of situation. So since that guy on the left there, it's going to the base. The water here is going to act as the acid and donate the H plus, and that sometimes can help you maybe visualize what you'll get on the other side. We're basically just popping an H plus onto the one here on the left. And you can really put that anywhere you want. I'm just going to put it at the end. So instead of NH2, I'm going to go NH3. Remember as well, it's not just the hydrogen, but it also is the plus. So I got to add the plus on there as well. And that is also when water sort of gives away its H plus, right? That is how we are in this case generating the hydroxide, which makes this thing a base. So again, putting the water here in the reaction can kind of help you maybe figure out sort of what's going on there on the right-hand side. Now that we have that, we could go with our 0.15 zeros. Change minus X plus X plus X. And here at equilibrium, 0.15 minus X, X, and X. Once again, here, I know water is not involved in the equilibrium, right? So don't put anything there so you don't try to use it incorrectly. I obviously here could write our KB expression, which would be our products here, C2H5, NH3 plus, and our OH minus, all divided by our original weak base there, C2H5, NH2 in this case. That is going to equal our 5.6 times 10 to the minus 4. Here we're going to go in, and that will get us x squared divided by 0.15 minus x equals 5.6 times 10 to the minus 4. You could assume x is equal to 0, and I think it's not so good, right? Bad. I think it's like 6% or so. So it is a bad assumption here. So again, a reminder, you should make sure that you do check. Just don't go like on autopilot and assume that they will all work. So let's go back now since it's a bad assumption here and solve it. So I'm just going to pop it here on the next slide. I think it was 0.15 minus x equals 5.6 times 10 to the minus 4. All right, clearly here I'm going to multiply this to the other side, and that's going to give me x squared is equal to 0.15 times 5.6 to the minus 4, 0.000084 minus 5.6 times 10 to the minus 4x. Now I'm going to bring everybody back to the same side, and that's going to get me x squared, going to be a plus 5.6 times 10 to the minus 4x minus 0.000084, right? Yep, 84. There you go. And that's going to equal 0. That's going to be, again, our A, B, and C here in our quadratic. So putting that in there, minus B, minus 5.6 times 10 to the minus 4, plus or minus the square root. We do everything in the square root. That's 5.6 to the minus 4 squared, minus 4 times A, which is 1, times C, which is negative 0.000084. That gets us inside the square root 0.000336314, to which if you square root it, 0.01834, we'll call it, all divided by 2 times a, which is 2. So that's going to give us 2x values in this case. We're going to go negative 5.6 to the minus 4. Maybe it helps if I hit that number, minus 4 there. Plus 0.01834 divided by 2, 0.00889. We go the subtract root, negative 5.6 to the minus 4 minus 0.01834. That's going to be negative all day, so that's not to be so great here. Negative 0.00945. Obviously here, this one is no good because if we go back to our table, we are interested here in X and we cannot have a negative concentration. So I would say the positive one there, 0.00889, 0.00889 molar should be the correct one. Also, again, really important, super common error. Again, this is the hydroxide concentration, not the H plus concentration. So this is the hydroxide concentration. So I got to go POH first, minus the log of 0.00889. And that is going to get me here. I'll call it 205. 2.05 as my POH. To get to my pH, obviously 14 minus our 2.05. And we're going to get here, probably do 14 minus that, so it minus itself, like 1195. That is a basic pH, which would make sense as this is a base. Once again, if you screwed up and you thought this was your pH, it should not make sense to you because obviously we're dealing with a base in this case. So again, these are things you want to think about as you go through the calculation. Any questions on any of that there? All right, so good weak bases, same as weak acids, ice tables, and it should get you the right one. So as we saw here with our weak acid, we could have a weak acid association gives us a Ka value. We could have a weak base that reacts for something like water, for example, to produce hydroxide, which gives us a Kb value. Now, if we were to add both of these reactions together, we would cancel out a bunch of things. We'd cancel out like that. We'll cancel out that. And we would be left with actually water. Yeah. And that would get us basically water. So your Ka and a Kb, when you add them together, basically gives you water because they're almost like the reverse of each other. By the way, when we add reactions with K values, what do we do with the K values here? We multiply them, right? We don't add them, so we multiply them. And that, by the way, gives us a relationship which is really important. That Kw equals Ka times the Kb value. So if you need a Ka value and all you have is a Kb value, you can use Kw, which is the same value we used earlier on, which is our 1 times 10 to the minus 14 value that we saw. And you can use that to convert it, or vice versa. If you need a Kb value, but you have a Ka value, you could use Kw. You may be asking yourself, why would you want to use that or need that? The answer is because there will be certain problems that we will come across where, frankly, they will give you the wrong K value. They'll give you a Ka value when you actually need a Kb value, and they'll give you a Kb value when you actually need a Ka value. So you could use Kw there as a way to reverse it. How do I know which one do I need to use? Good question. So the one that you need to use depends on your equation that you write. And if you write the equation correctly and you see on the product side H plus or H3O plus, you should be using a Ka value, yeah, regardless of what's given to you in the problem. And again, this is why being able to write these reactions are quite important. So if you write the equation or see the equation H plus, H3O plus on the product side, you should be rolling with a Ka value if you're doing some type of calculation. Just like if you write an equation there and you see hydroxide on the product side, That is a base situation, and you should be using a KB value. So that's a very easy way to determine which K value you should be using, because like I said, there are going to be problems along the way that you will be given a K value, and it will not actually be the correct one that you need for the calculation that you have to do. So looking at your equation that you wrote, or the equation, if it happens to be given to you, seeing either H plus, H0 plus, Ka, Kb, OH minus. Any questions on that there? All right, so now we're going to talk a little bit about acid strength and ways to compare acid strength. And it does depend on, for example, the type of acid that you have. So the first type of acid we're going to talk about is a acid with no oxygen. So when you're dealing with an acid with no oxygen, for the most part, most of those are going to be group 7, HF, HCl, HBr, HI, and so forth. Now, you may think that acid strength is actually in this situation based on something like electronegativity, right? Electronegativity increases as you go up and to the right on the periodic table. Fluorine is the most electronegative element you could have. And in this particular case, when you're dealing with acids that do not contain oxygen, the actual thing that is the overwhelmingly determining effect of which one is the strongest is what is known as bond enthalpy or bond strength. And bond strength is really the thing that determines how strong or weak an acid is. And here's a table of some bond enthalpy or bond strength. Now, why would that make a difference in terms of something being a stronger acid or a weaker acid? If you think about just the basic definition of an acid is it's got to release that H plus, right? So that's your definition. It's got to get rid of that H plus. So in order to release it in this case, it's got to break that bond. And if it takes a lot of energy to break that bond, it's going to be much harder to let that H plus go, right? If it takes less energy to break that bond, the H plus is just going to pop off with not a lot of problem, and that's actually going to make it a stronger acid. So when you look at something like group 7 there on the periodic table with all those acids, we actually see bond energy increase as you go up in the group. And that is why HF is actually the weakest acid out of that group. And actually HI, which doesn't get a lot of play, we always think about HCl, but HI is actually the strongest acid there, as it is much easier for that H plus to come off. So HCl, HBr, HI, those are strong acids. Doesn't take as much energy to release that H plus, so it's going to be able to do it a lot easier. HF is a weaker acid because it's met that kind of energy threshold where it's not as easy to kind of release that hydrogen. It's not going to release as much. So when you're comparing acids with no oxygen, you want to look at bond energy. The stronger the bond, the weaker the acid, the weaker the bond between the H and whatever it's attached to, the stronger the acid it would be. Any questions on that there? Now, when we look at the periodic table, you can also see here it increases, acid strength increases as you go down and to the right on the periodic table, and base strength actually increases in the other direction. When you look at acids that do contain oxygen, these are sometimes referred to as oxyacids because they contain oxygen. And most oxyacids will have this OH group on it. And this OH group, as you remember, maybe from bonding, is a polar group with the oxygen being more electronegative and the hydrogen being less electronegative in this case. And it has a polar bond already with this OH group. And it is this hydrogen that comes off that is what makes this an acid. And if you have a diprotic acid, it probably has got 2 of those. And if you have a triprotic acid, it's got 3 of those OHs hanging out there somewhere on the compound. Now, when we look at an oxyacid, we do look at 2 different things, and it does depend on the situation as to what you should look at. The first thing that we look at, or one of the things that we look at, is electronegativity. And a reminder again, that is the ability of an atom to bring electrons towards itself. And once again, on the periodic table, up and to the right there, it increases, right? Again, with fluorine being the most electronegative element you could have. The other thing that we sometimes look at is oxidation state or oxidation numbers, like you maybe did when you were doing redox reactions there and balancing redox reactions in 200A. You look at the oxidation state of things. And some cases we do look at electronegativity, and some cases we do look at the oxidation number. And let's take a look at why we would look at one versus the other. So for example, here, if we look at these two oxyacids here, chloric acid, bromic acid here, again, they both have the OH group here. And this is the bond we want to break, basically. And already this bond is weakened by the fact that it is a polar bond. Again, the electrons are kind of closer to the oxygen to begin with, and not so much near the hydrogen. So if we look at the oxidation state of the center atom, the Cl or the Br, we could assign oxidation numbers. Perhaps you remember oxygen is -2, -2, -2. Hydrogen is +1. That is a -2, -2, -2 is -6, +1 is -5. Overall charge here is 0, which means the bromine here is rolling with a +5 oxidation state in this case. If you do it for the chlorine over here, -2, -2 for the oxygens, +1 for the hydrogen. The chlorine here is also rolling there with a +5 oxidation state. So in this particular case, our central atom both have the same oxidation state, which means you can't really use that to compare the two because they have the exact same number, basically. So in the case where your central atom has the exact same oxidation state, what we look at then is electronegativity. And electronegativity increases as you go up the group. So chlorine is more electronegative than bromine. So what does that mean? Well, chlorine is going to basically, if you want to think about it, the electrons are already heading in this direction, but now the chlorine, because it's more electronegative, is going to make the electrons kind of head further in, if you will. And what that's essentially going to do to our OH bond here is going to weaken it and allow this H plus to come off a lot easier than the electrons heading in this direction. Bromine not pulling them in as much as chlorine would. It's not going to be as weakened and going to hang on a little tighter than we would expect here. So in this case, because chlorine is more electronegative, we would actually expect this guy in comparison to be the stronger acid of the two. Any questions on that there? If you're not sure about oxidation numbers and states, we'll do a whole chapter on it later on in the semester. But good thing to remember is oxygen is typically -2, and there's usually those guys in there. Hydrogen's +1. It needs to add up to the overall charge, which in this case both are neutral. So you could add them up, and that gives you there. As you might also remember, hopefully the oxidation number or state is different than the ionic charge you associate with something like chlorine and bromine, which we associate with negative charges. And that's not the case in this case because there's not actually a transfer of electrons. They're sharing electrons in this case. Now, when we have some acids, like a bunch of these chlorine acids, we want to look at the central atom. And obviously, the central atom in each of these cases, they are all chlorine. And because of that, they all have obviously the same electronegativity, right? They're all the same element. So we cannot look at electronegativity in this case as really the thing to look at in terms of strength. So in this case, we need to actually look at the oxidation number of each of the chlorines in this case. And they will have different oxidation numbers. So if we look here, oxygen -2, hydrogen +1, gives you a -1. So the chlorine here is +1 to balance it out. -2, -2, +1. That's -4 and +1 is -3. Gives us a +3. minus 2, minus 2, minus 2, and plus 1 is the one we just did. Gets us a plus 5. And over here, minus 2, minus 2, minus 2, minus 2, minus 8. Plus 1 gives us a minus 7. And that gives us a plus 7 in terms of the oxidation state. It is kind of the same idea. Once again, we have that weakened kind of OH bond because it's polar to begin with. So the idea here is the greater the positive oxidation state, that is going to suck the electrons closer in and once again weaken that bond more than somebody with a smaller positive charge or oxidation state. So in terms of strength, this guy would be our strongest at plus 7. Next guy would be our plus 5. Plus 3, and our weakest of the bunch here would be the one that's only kind of pulling the electrons in with a plus 1 attraction in terms of their acids. Any questions on that there? So essentially no oxygen, bond energy is what you're looking at. Stronger the bond, weaker the acid. If you're looking at some type of acid with oxygen, if we have the same oxidation number on the central atom, then you look at electronegativity. And if you have the same electronegativity on the central atom, then you look at oxidation number. Any questions on how to compare any of those? All right, the next thing we're going to talk about is actually salts. And one of the things, hopefully you know, right, is if you take an acid and you react it with a base, you make two things, right? You make a salt and water, right? And a salt is really just an ionic compound that actually comes from, obviously, an acid and a base. So if you think about a salt, and when you see a salt, you should think about it as, you know, it came probably from an acid and base at some point. And what would those acid and base means? The relationship here is really important. And the relationship I'm talking about is that relationship we talked about the other day, which is the relationship between an acid, for example, and its conjugate base. And as you remember, hopefully, if you have a strong acid, its conjugate base is going to be relatively weak. And if you have a weak acid, its conjugate base will be relatively strong. And that also works for our base and its conjugate acid. If you have a strong base, it will be relatively weak conjugate acid. If you have a weak base, it'll be a relatively strong conjugate acid. And that's really, really important, that relationship, when you look at salts and when you deal with salts. And if you remember, as we talked about, if something is sort of a strong in this sense, it has the ability to react with water. And in certain cases, your salt may react with water, and it may react with water in the way that it will accept an H plus, which means the salt would be acting as a base in this case. And the result of accepting the H plus from the water is you will produce hydroxide, which will make the solution basic. The other option is the salt could actually, in some cases, donate DH plus over. The result of that is you will make H3O plus, and this solution most likely will be acidic. Now, you could also have some salts that are weak, and these salts will not react. With water and basically are considered neutral salts. So it's important sometimes when you're dealing with salts, as I mentioned, to kind of think about where that salt came from in terms of, will it react or will it not react? And then also think about, how is it going to react with water? These reactions, by the way, when it reacts with water, these are sometimes referred to as hydrolysis reactions. Yeah. So hydrolysis reactions, again, is going to be a salt that's going to react with water and maybe produce H3O plus or maybe produce additional hydroxide. Obviously, producing H3O plus or hydroxide will have an effect on the pH of that solution. So let's start with the first type of salt, which is a neutral salt. And neutral salts contain metals from group 1 or group 2 on the periodic table. If you remember our conversation, group 1 and group 2 on the periodic table are pretty much where our strong bases come from, which means it will not go through hydrolysis because it came from something strong, basically, essentially, except for beryllium. So if you take a salt like sodium chloride, and a salt like sodium chloride most likely came from two things. It probably came from what acid? It probably came from NaOH, which would be our base, and what acid? Probably HCl. Yeah, that makes sense. So HCl, which is our strong acid, sodium hydroxide, which is our strong base. That is probably where these guys came from. So when you're looking at the salts, you want to think about, much like what we see here, what are really the two ions that that salt's going to do? Because it's an ionic compound, because it's floating around basically in the solution, it's going to break apart into those ions. And it also has a lot of water in that solution available to it to react if it wants to. So when we think about the sodium, it came from sodium hydroxide, which is group 1 or group 2 on the periodic table, which means it's going to be relatively weak and it will be neutral. So like a pH of 7 in this case. We would not expect it to continue to react with water. It's just going to swim around, not really do much. Same thing when we look at the chloride. The chloride most likely came from hydrochloric acid, which again is a strong acid, which means the chloride is going to be relatively weak and also would be considered a neutral salt with a pH of 7. So if you have a salt that basically contains, like we do here, two parts that came from both a strong acid and a strong base, you would expect that salt solution to be neutral and have a pH of 7, as there would be no hydrolysis reactions happening. So these guys are not going to go on and react with water in this case. Any questions on that there? Now let's take a salt that maybe will do something. Let's see. Let's take a salt like sodium acetate. Yeah. So if we take a salt like sodium acetate, when it breaks apart, it's going to break apart into a sodium ion and an acetate ion. So if I had to, again, take a reasonable guess as to where my salt came from, the acid most likely would be, if it makes acetate, the acid probably would be acetic acid, yeah. So it probably comes from acetic acid. And acetic acid is what type of acid? Strong or weak? It is weak, and I know that because it's definitely not one of the 6, right? And it is the most popular weak acid people like to use in examples. The sodium probably came from sodium hydroxide, right? Which is a strong base, right? So these are really probably where both of these things came from. So when we look at this salt, which is the sodium acetate, we know just from our conversation a second ago, obviously, this comes from sodium hydroxide, it's group 1 or 2 on the periodic table. It is going to basically be neutral. It is not going to go through hydrolysis. And it is not going to go through hydrolysis. So now we need to take a look at our acetate in this case. And our acetate did come from over here, our weak acid. And because it comes from a weak acid, it is going to be relatively strong. And it is going to go through hydrolysis here. So it is going to react with water. So how do I know how it is going to react? It is going to react because it came from a weak acid, which means if it came from acetic acid, which is a weak acid, the acetate should be its conjugate base, right? So that is the relationship. Yeah. Yeah, the salt that's produced from that reaction will not continue to react with water at that point because they're relatively weak, so they will not continue to sort of react with it. Yeah. At this point, we do know it's going to be its conjugate base, and that's really helpful if we want to write the actual hydrolysis reaction. So I'm going to take my acetate, I'm going to react it with water, and once again, this is going to act as a base. So the idea here is it's going to do a Bronsted-Lowry base, which means it's going to accept the H plus, and that means it is the water in this case that's going to send the H plus over because it will react as a base with water. The result of that is you will always get, so if you're not sure, you will always get where it came from. So when you put that H plus back on, you get our acetic acid back. So when a salt reacts with water, it will always produce sort of where it came from. So if you could sort of figure out, I think it comes from acetic acid, that is what you're going to produce. But more importantly here, we are going to produce hydroxide. So without even doing a calculation, this solution should be acidic, basic, or neutral. This solution should be basic because we are producing free hydroxide in solution. To do a calculation, no surprise here, this would be a ice table, yeah? And when you solve for X in this case, it is going to equal the hydroxide concentration. Again, not the H plus concentration. This will get you your POH to your pH. By the way, when I do my ice table calculation, what type of K value should I need? Ka, Kb. I would need a Kb value. Probably you will have a Ka value given to you. So this is the type of problem, hydrolysis problems, where they give you the wrong K value. And that is where you can use what we talked about a second ago, the Kw equals the Ka times the Kb. And you could convert it out to your Kb value in this case. So a salt that comes from a weak acid is considered a basic salt, and it will react as a base when it reacts with water, and again, it will produce that hydroxide. I feel like it's got an extra H on that it shouldn't have. And again, you will need your ice table, and that will get you to your Kb and your OH minus and your POH and your pH in that case. Any questions on that there? So we have neutral salts, we have basic salts. I feel like there's another salt. There probably is. There's obviously acidic salts as well. And acidic salts actually come from a weak base. Yeah. So if we take something like ammonium chloride here, ammonium chloride, as you can see, will break apart into NH4 plus and Cl minus. And in this particular case, this NH4Cl most likely came from the reaction of hydrochloric acid plus some ammonia. These are probably the two things that it reacted. This is going to be our strong acid, and this is going to be our weak base. So once again here, when we look at both parts of the salt, we can probably eliminate our chloride because once again, it came from our strong acid, which means it's going to be relatively weak and really be a neutral salt and will not go through hydrolysis. So again, anything that comes from something strong will not go through hydrolysis, is considered neutral. It will not react with water. But our NH4 plus here obviously comes from NH3, which is a weak base, which tells us that that NH4 plus will go through hydrolysis and will react with water. So how is it going to react with water? Since it came from a weak base, the NH4 plus is essentially its conjugate acid. And when it reacts with water, that is how it's going to react. The NH4 plus will react with water as a acid, which means it is actually the one that's going to send the H plus over to the water. The result of that is we will then produce where it came from. As I mentioned before, you will always produce where it came from, which is NH3. And when that water gains that H plus, a little H3O plus, And once again here, without even doing a calculation, because we are producing H3O plus, we should know that this solution should be acidic, and this solution should be acidic. If we wanted the pH of this solution, we would again do an ice table, and we would solve for X. X in this case actually does equal the H3O plus, which means you can go directly into your pH equation after you do that. And just like the one we talked about a second ago, you most likely will not have the Ka value given to you, which is what you actually need to use here because you produce H3O plus. So once again, you very commonly will have to use that Kw to kind of go from a Kb. You most likely will be given the Kb value of NH3 in this case, and you would have to convert it into the Ka value and solve for it. Any questions on that there? Yeah.
Yeah, how do you determine whether it came from a strong acid or like a weak acid or vice versa?
I would say you would first have to sort of determine what it came from to begin with. Yeah. So all salts, right, pretty much come from an acid and base reaction. So you have to think about sort of what acid or what base could most likely make that particular salt. And once you do, then you got to identify the acid as either being one of those six strong, or if not, then it's a weak, right? And then you know that. And the same thing with the base part of it. If it comes from group 1 or group 2 on the periodic table, it's essentially neutral. Yeah. So if it's not group 1 or group 2 on the periodic table, you might have something that comes from a weak base. Remember as well, most weak bases, as we saw there, right, have nitrogen in it, right? So again, if you see something with nitrogen like we see here, with our NH3, you know that it probably will be a weak base. Any questions on that there? Now, there is also one more way that we can actually get a acidic salt, and certain metals, especially transition metals, that have a +2, +3 charge, a larger positive charge, can also behave like an acidic salt. So for example, if you had something like our aluminum here, and I'll just erase all my scribbling on the page here so we can kind of see it. Yeah, something like this. This is a complex ion, which in a later chapter you will know how to name that, but that is a complex ion basically of aluminum that has a +3 charge. It has 6 waters attached to it. And I'll just draw out one of the waters. By the way, the waters are attached to the metal through the oxygen in each of these cases. And in this situation, what actually happens is another water that's just coming by, not attached to it. And by the way, that is really what we mean when we put aqueous next to something. That's what ions are in solution. They're hydrated with waters a lot of times surrounding them. When another water comes by, it actually is going to pluck off one of the hydrogens on those waters that are attached to the metal in this case. When it does so, that is going to create our H3O plus in this case. And that is what's going to make this solution acidic. If you're just kind of keeping track of how we get to this scary looking thing here, you could just look at my badly drawn picture. But if we look at it and we see basically here, we have 1, 2, 3, 4, 5 intact waters. So nothing happened to those 5. When this guy loses the hydrogen, it is left with an OH minus, which happens there. And because that's OH minus and the original guy had a +3 charge, +3 and -1 is +2 left over, basically. So that's how we get to that big guy that is there, which you also know how to name later on in a later chapter as well. So this is another sort of example, certain metals. And like I said, I would say traditionally, or in a lot of cases, transition metals can do this. Things like copper can do that +2 charge and that are hydrated. As we'll learn in a later chapter, something like water in this case is what's known as a ligand, and that is a Lewis base. And we'll talk about what those are a little bit later on as well. Any questions on salts here? All right, so let's take a look here. Okay, so let's take a look at our KCl first off. That is a salt. And again, when you're looking at a salt, what you want to think about is really the two parts of it, which is potassium and chloride in this case. And once again, if you're not really sure just by looking at it, you might want to think about where it might have came from, what acid-base combination could give us that. Perhaps you will know, right? HCl seems like a good one for our Cl, and maybe something like KOH, right? Which is potassium hydroxide, is most likely our acid-base sort of combination that got us here when they do a little double displacement sort of deal, right? And those guys come together basically to make our KCl. Now, HCl, as we talked about, is a strong acid, which means we do not need to worry about this guy, right? He's not going to go through hydrolysis. KOH is a strong base, and also K is group 1 on the periodic table, which also says it will not go through hydrolysis. No calculation needed. This is a neutral salt, which has a pH of 7 in this case. Any questions on that one there? All right, let's do one where maybe there is a calculation. Here we go. Try this one. Consider 0.3 molar sodium fluoride. Ka value for hydrofluoric acid is 7.2 times 10 to the minus 4. What is the pH? Okay, so let's take a look since we're getting to the end here. We have a salt, which is our NaF. So that will break apart into a sodium ion and a fluoride ion here. And again, we want to analyze really our salt to see if anybody's going to go through hydrolysis. So we've talked about a bunch at this point. That probably came from sodium hydroxide. It's group 1 on the periodic table. So we really don't have to worry about the sodium going through hydrolysis. Now, F minus came from, and a lot of times in these problems, you have a lot of information sometimes people just overlook, which is I see HF, I see KA. That tells me this guy probably came from this guy over here. And I know it's a weak acid because there's a Ka value. And because it came from that guy, which is a weak acid, I know that this will act as a conjugate base and will go through hydrolysis. So it is the F minus in this part that is going to go through hydrolysis. That is where we want to start with our equation. And it is always going to react with water in this case. And again, understanding where it came from, that it came from an acid, it's going to act as a base, will tell me it's going to accept the H plus. By the way, common sense also tells you it doesn't have an H to give, so it cannot give an H plus it doesn't have, so it's got to accept in this case. As I mentioned before, sometimes people struggle with the equation. Looky there, I don't even have to struggle. It's right there. I could just write what that is, right? It is always going to produce where it came from. Here it's going to release the H plus from the water. That is going to produce hydroxide. So again, before I do my calculation here, I should end up with what type of pH? Should end up with a basic pH. So again, these are things you want to think about. We're going to initially here go 0.3 molar for our F minus, and that is because it is a 1-to-1 relationship between these two. So the concentration of the F minus is 0.3 molar. By the way, the concentration of the sodium is also 0.3 molar, but you don't really need it in this case. Going to go 0, 0. Change is going to be minus X plus X plus X. Gonna go 0.3 minus X, X, and X. First off, any question on the table there? This is going to go into our equilibrium expression of our products over our reactants. Once again, not going to include the water, obviously. By the way, this is a K what? A, B, C. It should be a KB once again. Am I given the KB in this case? I am not. I am given the Ka. So you do not want to use the Ka value here. We do need to get to the Kb, which would be Kw divided by the Ka. So that is our 1 times 10 to the minus 14 divided by 7.2 times 10 to the minus 4. That's going to give us the Kb that we actually do need to use in this calculation. And this is again the type of problem which historically will give you the wrong value in a sense. 1.4 times 10 to the minus 11. So now we could actually solve this like normal. We'll put our x squared, our 0.3 minus x equals 1.4 times 10 to the minus 11. I'm going to assume x is equal to 0. That's going to give me x squared, 0.3 on the bottom equals 1.4 times 10 to the minus 11. Once again, I'm going to multiply, then square root it. And that will get me here, if I hit the right button, maybe. There we go. A little square root action. Wow, that's a lot of zeros. Too many to count at this late hour. There we go. That's gonna give me, I'm gonna go, I'm gonna write about here maybe. X is equal to 2.04 times 10 to the minus 6, looks like. We do need to check it, so I am gonna divide that by 0.3. I'm gonna times it by 100, and we're perfectly good. We're like 0.006%. So the check here is good. Again, a reminder that at this point, that is the concentration of my OH minus, again, not my H plus. So that means I could go into my POH minus the log of really my X value there, 2.04 times 10 to the minus 6. And 6. And that's going to give me a 5.69 POH. So once again, if you understand what's going on and you got that and you thought that was the pH, should not make sense, right? So it should be basic. So we do have to do our 14 minus 5.69. And we got an 831. That sounds more basic. So 831 is definitely a basic pH, which is what we would expect in this case. Any questions on that there? All right, we're laying up there for today.